We're going to finish up talking about transformers and induction. And a transformer is a very important device that is used in many situations. This is actually a type of transformer that converts AC to DC and DC to AC current. It turns out in Europe the current's DC. In the United States it's AC. So if you have a United States device, you have to have this special transformer. This changes voltage values also from one value to another, and this is actually what we're going to talk about more than the conversion of AC to DC or vice versa. The plug-in transformers frequently are used also to convert 120 volt AC into the 3 to 12 volt DC range. So let's look at how these work. Before we do that, however, let's take a look at why transformers are so important. A power plant produces energy at a very high voltage. It is actually stepped up to an even higher voltage for the purpose of transmission. This higher voltage is necessary in order to carry it through multiple miles of line to get it from the power plant to various areas of the country. And then because that high voltage is quite dangerous, it's then stepped down to a lower voltage before it's taken into a home. And so these transformers are important, an important part of the production and transfer of the electrical energy from where the energy is produced to where the energy is used. So how does a transformer work? Well, it's as simple as this. You look at on the left of this is what's known as the primary coil, and on the right is what's known as the secondary. And the voltage that comes into the transformer is called the VP, or primary voltage. Then there are a certain number of turns, NP, in the primary. Then there are a certain number of turns, NS, in the secondary. And then the produced voltage in the secondary, which is called VS. And so this is how it's constructed. And the formula for this is as simple as this. The voltage out divided by the voltage in is equal to the number of turns on the outside divided by the number of turns in. Another way to look at this is the secondary voltage divided by the primary voltage is equal to the secondary number of turns divided by the primary number of turns. And so this ratio carries on, and it's also true for amperage as well, except that because of the relationship between amperage and voltage, it's inverted in terms of the primary divided, or the secondary divided by the primary is equal to the primary divided by the secondary when you're talking about current, and when you're talking about voltage, both secondaries are on the top of the fraction and both primaries are on the denominator of the fraction. Now, a transformer that increases the voltage is called a step-up transformer and has more coils in the secondary than in the primary. And one that decreases the voltage is called a step-down transformer and has more coils on the primary than the secondary. So let's look at a couple of problems with the step-up and step-down transformers. What is the voltage output of a transformer used in a rechargeable battery? The primary has 500 turns, the secondary has 4 turns, and the output voltage is 120. Well, if you convert, you start out the secondary voltage, or the primary voltage divided by the secondary voltage is equal to the number of turns on the primary side divided by the number of turns on the secondary side. If you solve this for VS, this is going to equal VP times NS over NP. And so you see that if this is a step down, then this will be a smaller number than this. If it's a step up, it'll be a larger number. In our case, we have the input, the primary voltage is 120. The primary voltage is 120. The secondary is 4, and the primary is 500. So this is a step down. And you have 0.96 volts in the secondary. Now here in the second problem, you have a multi-purpose transformer that has a secondary coil with several points. The voltage extracted is different depending on which point these is. The input voltage is 240. The primary number of turns is 280. What are the numbers of turns of the parts of the secondary to produce the various outputs? And so, again, Vs is going to equal Vp times Ns over Np. Or, if you rearrange this so that you're looking for Ns, which is what they're asking for here, it's going to equal Np times Vs over Vp. So in the first case, it's 5.6, so it's going to be 5.6 over 240 times 280. So Ns in that case, 5.6 divided by 240 is going to be quite a bit smaller. It ends up being 6.53. Well, we'll just say 6 or 7. In the second one, so what are the number of turns of the parts of the secondary to produce these outputs? So the second one, you want to have an output of 12. So now you're going to put 12 in here, divided by 240 times that. And then in the third one, you're going to put 480. And so in each case, you're going to just change the numbers. Now the amperage, it says if the maximum input current is 5, what is the maximum output currents of each? And so again, you take the formula that we had before, and Is, so this is the output, is going to equal Ip times the primary divided by the secondary. So we will end up with the same, if we do the calculation here, or rearrangement here, this is going to now be, instead of the secondary, it's going to be the voltage primary over the voltage secondary. And again, if we put the 5 as the input current, and we put each of the coils, in the first case we found 6.53 for the, the voltage. We put in 5.6 for the secondary voltage and 240 for the primary voltage. So this first one, 240 over that times that, you're going to get an amperage of about 214 amps. And then you do each one of these the same way that you did. Finish up by talking about let's finish up by talking about induction. And inductance is actually the ability of one device, in this case coil 1, to cause a current in another device. Now obviously if you have amperage going through, or current going through coil 1, it induces a magnetic field that goes through coil 2 and induces a current in coil 2, and that's inductance. Mutual inductance is the effect of Faraday's law for one device on the other. These coils can induce EMFs on one another like an inefficient transformer. Their mutual inductance, M, indicates the effectiveness of the coil of the coupling between them. Here, a current change in 1 is seen as induced EMF in 2. Notice that current change, it has to be a current change. EMF2 is equal to M times the inductance in 1 over time, or excuse me, the change in current over time. A heating coil for a clothes dryer can be counterwound so that their magnetic fields cancel each other, greatly reducing the mutual inductance in the case of a dryer. The symbol for inductance is shown at the top here. And there's self-inductance. And self-inductance is the effect of the Faraday's law on the device on itself. So self-inductance is, again, the change in current divided by the change in time times the L, or self-inductance. And in this case, it can be calculated from something called mu zero, which we had a couple of chapters ago, times n squared. That's the number of turns, times A over L. An inductor is a device that exhibits a significant amount of self-inductance. When you rapidly switch an inductor on and off with 1.5 volt batteries, it showed to induce EMFs of several thousand volts. These voltages can be used to store charge in a capacitor for later, such as the camera flash attachment. Two coils placed next to each other have the mutual inductance of 0.5 of a millihenry. What voltage is induced in one when a 2 amp current is switched on and off over 30 milliseconds? Remember, the current, it has to be a change in current over time. So constant current doesn't produce mutual inductance, but E is equal to M times delta I over delta T. And we have M given as 5 times 10 to the minus 3 henries. Oh, that's pretty bad. Let me try to write that down again. That one's not too good. Let's try that again. 5 times 10 to the minus 3 henries times delta I, which is 2 amps, over delta T, which is 3 times 10 to the minus 2 seconds. And if you do the calculation here, you get 1/3 of a volt, or 0.333 volts. The second problem has a self-inductance. A device turned on and 3 amps flows through it in 0.1 milliseconds later. So you turn it on and there's this change that takes of 3 amps that takes place over 1/10 of a millisecond. How much self-inductance is generated in this device? And you have E is equal to L, which is the self-inductance, delta I over delta T, and if you rearrange this to find L, E is equal to 100, it's going to be E times delta T over delta I. And E equals 150 times delta T, which is 1/10 of a millisecond, or 1 times 10 to the minus 4 seconds, divided by 3. So the self-inductance here is 5 times 10 to the minus 3 henries, or 5 millihenries.